Boom! Now we're recording. What's up? I'm Austin Griffith. I'm here with Carlos and Etta, and we are going to do an intro to EVM today. Not a deep dive, but just like, what the heck is this EVM? How does it work? What are these opcodes? What's this bytecode? We want to get in and learn about it. I think I'll take over and do a high level, but how are you guys doing? How you doing, Carlos? How you doing, Etta? Excited for some EVM stuff? This is going to be all Carlos. Carlos is going to teach us, right, Etta?
I mean, this is like episode 2, and we are already going hardcore with
Let's
the
go
EVM.
into EVM.
Yeah. That's like what you get when you see like when you watch BG Labs.
Yep.
Everything is an experiment, right?
Yep, exactly. Yep, trial and error. Okay, let me steal a screen and let me go with, there we go. So the thing I wanted to show off is kind of like this idea of the difference between the execution layer and the consensus layer, right? So if we have, oh no, that's the wrong thing. Wait, how do I undo? Is there an undo button here? Oh man, I don't think there is an undo button. Okay, this is going to be Bitcoin. And this is going to be Ethereum over here, right? This is the cool ETH. Okay, so at the base layer, right, everything is just talking peer-to-peer, right? You have all of these nodes that are connecting, and there's thousands of these nodes, and they are talking peer-to-peer. So each one of these has like 50 different peers that it talks to. There's no single person in charge. This is the consensus layer. This is basically the network layer. And then on top of that is this sort of like chain of blocks. I can also hear my cat snoring back here. Hopefully you guys can't hear my cat snoring. But each one of these nodes on the network is keeping track of their own chain of blocks, right? So this whole chain of blocks is stored on each one of these machines. Each of these machines are talking peer-to-peer to each other. There's no central controller. If there's a central controller, finding a consensus would be really easy, because that central controller could just say, here's the consensus, here's the thing, here's the best block, right? But if you imagine that this whole network is very spread out, and then this dude way over here mines a block, at the same time this dude way over here mines a block, then you've got two different blockchains with two different heads just for a second, and it's hard to figure out which one to go with, right? Finding the consensus of which of these blocks are the actual chain. We follow the longest chain, but that's the consensus layer. Basically, all it's doing is packaging up transactions. Inside of this block, these are transactions. Tons and tons and tons of transactions, and that's what we're packaging up here. We're coming to a consensus about if these blocks of transactions are valid, right? And then at the very top layer, at the very top up here, the execution layer, Bitcoin is very simple. It's just a ledger of Alice, sends money to Bob, and now Alice's balance is this and Bob's balance is this. And then Bob sends money to Charlie, and then Charlie's balance is this and Bob's balance is. And it uses UTXO. We're kind of like from a high level talking through this stuff. But basically, if we think of the execution layer of Bitcoin, it's just like this book. It's like this ledger that's like, okay, this person sends money to this person. And that's basically it. And you can go to your book and you can see how much money Alice has and how much money Bob has. And it's using this really, obviously very complex consensus layer to make sure that this very kind of like simple execution layer works the way it needs to. And when someone mines a new block, everyone across the network adds that new block and verifies it and makes sure all of these sends are valid and you didn't double spend or something like that, right? Over on Ethereum, we have the same thing, right? We have all these nodes talking peer-to-peer. They're all keeping track of a chain of blocks, right? And these chain of blocks are basically just packaged up transactions. Everything is a transaction, right? We have all these different transactions. They're all packaged up. But here's where it gets really interesting. Instead of a simple ledger, a simple book, we want to think of this as like a little computer, right? This is like a computer, and it has CPU power, and it has memory, and it has storage, right? So we take this transaction, Alice sends 5 to Bob, and we run it through our CPU, our little EVM, our little machine, and it processes some information. Sometimes it's not just Alice sends money to Bob, but maybe it's we update a storage record, or we process a bunch of information and store it, right? So the execution layer of Ethereum is this little virtual machine, this little tiny computer that acts like a normal computer, but it's very, very simple and deterministic. So instead of just a ledger, we have this computer. So what we're going to be talking about today is kind of like how the heck you translate these transactions into this EVM, and how this EVM sort of parses these transactions and what they look like. And if I jump over just for a second to look at the DAI stablecoin, we're going to go to Etherscan. We're going to go to the DAI contract. What I want to look at is first the contract creator. Here's a transaction. This transaction created the DAI stablecoin smart contract. And if we go look at it, we should, oh no, it's calling a function, darn it. What we need to see is an actual deployed contract with like, let's see, where even if I have deployed a contract, let's just go look at the block of transactions and let's go see if we can find a transaction. Oh man, with what I want to see is let's see, let's go back to this. Let's see, can I see to contract? Let's just go find the contract getting deployed. There we go. Okay, so again, think of everything as a transaction, okay? And those transactions are, to, from, value. In this case, the to is empty. It's not actually sending. In this case, it is sending, but when you deploy a contract, there's no to address. It ends up being a bunch of bytecode, this bytecode right here, right? So we send a transaction to no one, and it's full of all this information. This is actually the program. This is the program that's going to run. And there's probably even some things that happen after this that are some construction arguments that come into it. So basically, instead of just Bob sending money to Alice, we start keeping track of this little computer, and each one of these could possibly set up a new program. Each one of these green transactions could technically be a new smart contract. That's a new program. Then on top of all that, there could be another transaction that needs to call a function on one of these smart contracts. And that's also going to be a transaction. And that looks the same way. There's this weird data, right? But this is going to be a function selector. And we're going to put a bunch of data on chain that says the to address will be a contract that we want to call. And then this will be a function selector. And we'll say we want to call this function with these arguments. And we'll get into that in a little bit. I think, Carlos, you know way more about the EVM already, thanks to Winter's course and getting into it. But hopefully we can kind of cover what a smart contract code, what the code looks like, what that bytecode represents in terms of opcodes, and then also what function selectors look like and how we call functions on smart contracts. I don't know if you want to take it over from here. This is a wild view, but imagine like you have these blocks of transactions, everything's a transaction, and each transaction you process through this little EVM, and everyone on the network has their own little computer that they keep track of the current state, and they run each transaction through their little computer. Probably not the best way to explain it. What am I leaving out? You guys
I think this is amazing, like amazing introduction, and I love like the context, really.
Okay, awesome. Yeah. Let's dive in. Look, Carlos, you take it away, and let's get into like, I think you had this question of like, what is this? What is this 6.8? This stuff at the beginning of this contract, 608060. What the heck is that?
Yes. First, like I wanted to focus. You talk about like this like little computer. Sometimes if you go to ethereum.org, they see the EVM as the big computer, just like a unique, like a single instance of like this big computer. It's like a good mental model, if you like. But yeah, like you said, it's just like, this is just like every Ethereum full node like runs a copy, an instance of the EVM, right? And they are in sync, so you can see it as a like a big one computer. And as you said, it's like any computer, right? You have like storage, you have like memory, stack, and some other stuff that we will see. like Eda, like, do you want to see? I would love to hear what's like your mental model. Like when you think about the EVM, I mean, what do you think? It's like the same as Austin, like this like computer.
Yeah, so I was gonna say, like, I generally view it like the supercomputer where, you know, everyone has a program and can execute, and it executes on everyone's computer. So then you can say, okay, like then it's kind of a valid program. Yeah, but this is kind of my high level overview of EVM.
Yeah, that's nice. So yeah, this is you are seeing my screen, right? Yeah.
Yep.
So
Yeah.
this I took this from Ethereum.org, and it's just like a high level representation of the EVM. You see like like you have the memory, the stack that we'll see later, the gas, and the program counter, which is just like a pointer to the opcode that we are running at that moment. And then this is as you see here, is just temporary. This is just when you run a function in the smart contract, this runs and this is filled with data. But then at the end of the transaction, this is emptied. But here we have the storage, and this is like the like the big like storage where all the truth resides. When it says, okay, Austin has this NFT ID and it's saved there. This is like this like shared like global state, like the blockchain state, right? This is persistent. So I think like we could just like keep talking about the EVM just for the sake of talking about the EVM. But I think it's always nice to have like some kind of like mystery to solve, or like a game to play or something like that. I don't know. So my idea was like, I don't know if you have realized this, but if you check, I mean, you just like saw it just before, like Austin, you were showing like this like call data, and you will see that the beginning of the contract deployment, the bytecode of that contract, all of them start with this sequence of numbers. I mean, I put like all in quotes because sometimes this 80 is like a different number, but the other digits are the same. So have you realized this, like Eda or Austin, that if you check like the bytecode when you compile a smart contract, you will see that always you have like these hexadecimal digits which are always the same. So I think this is like a good excuse, just to try to figure out why that's the case, and it will be just our excuse to see all the EVM details. What do you think?
Sounds great. Yeah, I've seen it a lot, but I have no idea what it is. I feel like it's just like an identifier, like a function selector, but for all of like this is the function selector that says these are contracts or contract version or something. I have no idea what it is, though, but I have seen it a lot.
We'll see. No spoilers.
Yeah, no spoilers.
Okay, so yeah, let me close this. Wait. Okay, this is the because can you see my text editor now? Okay,
yep.
Yes. Yeah. So yes. So first, like this computer, okay, the EVM, that as any computer, like the computers only understand like bits and bytes, right? Like they don't care about like your messy JavaScript code or your crappy Solidity code, because they don't understand that. That's why that's like a high level language, like you have Python, JavaScript, Solidity, whatever. That's why we have compilers, right? In the case of the EVM and Solidity, you have Solidity here, yes. And then when you compile Solidity, you get the bytecode. There's actually like a few more steps here. I think it's like Yule.
Yeah, Yule is I hear a lot of talk about Yule, but I don't understand it at all. Solidity goes to Yule and then it goes to bytecode. Is that right?
I think it's Yule, and then it has like another step called like more like a low level assembly, and then bytecode.
Cool.
So this bytecode, which is like the number I have here, this is like the number that we are at the beginning of the smart contract deployment, and these numbers was like the EVM understand, right? So yeah, one thing before going forward, I want to do like something I'm going to call like bits 101, because yes, you know that when you have numbers in your programming language, there is like different way of representing these numbers. We have like the decimal representation, which are the ones that we are used to, like 0 to 9, like any number. You have like binary, which is like just like 0 or 1. You have like a bit, which is 0, 1, and you have a byte, which is 8 bits. Yeah, like sorry for this introduction, but I think like some people may, maybe they won't know why, because to understand what like the, like the bytecode is, we need to understand what like a byte is and a hexadecimal digit is. So a byte is just like, you have, for example, this will be like a byte. And then we have like the hexadecimal digits, which is just like the 0 to 9. And then we have 5 more. And since we don't want to do like 10, 11, we are hexadecimal uses letters like this. So this is one question for you guys. So let's see if you can answer this question. How many, because here we have like 16, like from 0 to F, which is like 15. So how many bits do we need to represent any, hexadecimal digit? How many bits do we need?
Is it 2 bits?
No?
So let's see, 2 bits would give you 4. You need 16, right? So
yeah, you need actually 16,
8.
like 0, yeah.
Is it 8 bits?
No.
4
Half.
bits.
So
4
2
bits.
over 6.
Yes,
4 bits.
it's 4
Yeah.
bits. Yeah,
4
yes,
bits.
because it will be like the 0, and then here you will have like the F,
Yeah.
right?
Yep.
Which is
There
like
we go. Yep.
like the 15, it's the same. So sometimes in binary or hexadecimal, when you have like a hexadecimal number, for example, because if I tell you 60, if I don't say anything, you might think that this is like a decimal number. So sometimes in some for representation, you say like 0x. With a 0x doesn't say anything. It's just saying, okay, this number is hexadecimal. So, okay, so we need like 4 bits to represent like hexadecimal number. And another question is, with 1 byte, how many hexadecimal digits can you represent? This is an easy one. With 1 byte, which is 8 bits, how many hexadecimal? 2, right? Yeah, perfect. Perfect. 2. So we have this, this hexadecimal representation. So we can split into bytes, right? And we know that 2 hexadecimal digits is 1 byte. So we have this byte, this byte, this byte, and this byte, right? So now this is called the byte code for a reason, right? Because it is like a sequence of bytes. So any of this is just 1 byte in hexadecimal. So, okay. So the thing is now, how do we know as humans what these bytes represent, right? Because we already know that the EVM understand like these bytes, but we don't know. So it's like 60. Okay, so we don't have any idea what this 60 means. So for that, you can check like the EVM specification and the opcode. This is called opcodes, and you can go, for example, to the I think this is a nice resource. If you go to evm.code, you get like a mapping from all the opcodes in hexadecimal. You see like A, like 0A, 0B, like you have like all the opcodes and some what is like the instruction name and also like some description about what instruction what that instruction do. So for example, we have
opcode operation. Like each one of these are like operations you're doing.
Yeah,
on
like
your little
instructions,
computer,
yeah,
right?
operation. Yeah,
Yep.
yeah. So we have the 60, right? If we go back here, we have
There
like
it
the 60.
is. Yeah.
So we have 60. Oh, so we see that 60 represent push one instruction. And here you have like the description, an example, and you also have like the playground, which I would recommend that you go to the playground because you can just run some code and see how the stack and the memory changes. Is like a really nice resource. But for now, we will do it like manually. So, okay, we have 60. So, okay, 60 is push 1. So, okay, so we have push 1, and this is going to push 1 byte. No, sorry, 1 byte to the stack. And what is going to push is like the argument, which is like 80. And then we have, I will explain this later, but now we have another 60, which is going to be like another push 1, and we have a 40. And then we have a 52, which is the last opcode. And we can go here and see 52. It's Mstore. And this is basically saving some information in this memory offset, this value. This is what it's doing. So this can be translated to this, which is like way more readable, right? I mean, we can, maybe we don't know how the stack works yet, but you can see this is like, you can say what this is doing, but you can say, okay, this is pushing, and this is like storing something. It's like memory storing. Okay, so when you do this, when you do push one, this value, you are basically pushing to the stack, and the stack is just like you can think about the stack just like an array, but it have like this stack property that when you push things to the array, to the stack, you just put things on top. And when you want to retrieve data from that stack, you just have to undo the stack. You have your pop from the top, right? I think this is called something like, I think it's
first in, first out, maybe.
Or
last in, first out.
Yeah,
okay.
or yeah, something like that.
Depending
right?
on how your stack works. Yeah, you can pull from the bottom or the top, but basically think of it like a structure that's storing things, and you're like a stack of plates, right? And you need to get to the third one. You're gonna have to pull a few things off to get to the third one. Yeah,
that's right. So in this case, we are doing like pushing this value. So this is the value of the stack right now, 80. Then we are pushing this value, which is going to be on top. Okay, so this is already executed, and now the last part is the Mstore. And if we go to the Mstore instruction, you will see that it is taking this input, is taking two values from the stack, which we already have, right? We have two values on the stack now. And one of them, the first one, is going to be the offset, and the second one is going to be the value. So if we go back here, this is going to be the offset, and this is going to be the value. Like so in decimal is we can say this is like 64 in decimal, and this is like this, and this is like 128. Yeah. So also, like, now we need to talk about like the memory, right? Like if you remember like the graphic from the Ethereum.org, we have the EVM, we have the stack, and we also have the memory, which is like just another piece of the computer. And it's basically an array, not like the memory is just like a array of bytes, right? You are just like storing like random bytes in this array, and it has like a special feature, which is it only works in chunks of 32 bytes. So for example, if you want to write, this is like the initialized memory here, and you want to write like a byte here, you can do that, because this will, you can write only one byte. It works on these like 32 chunks. So this will be like something like all zeros, then the FF, and then all zeros. You need to initialize all the memory when you are like writing to them. Okay. So now what we are doing here, we are saying, okay, we want to store in memory in the position 64, on the byte 64, like the array on the position 64, this number, right? We want to store that number. So remember that these are hexadecimal digits. So this is 1 byte, 2 byte. So we need to do like 64, right? 64, which is going to be, this is 64, it's going to be 32 bytes, right? Yeah.
Yep. I see you have column right there. The column thing in your text editor lets you know that you have about 64, which is really nice.
Yeah. That's what I was looking at.
Yeah.
So you got 64. Yeah.
Yep.
So this is writing, since this is work on chunks.
That's a word size, right? The word size is 32 bytes.
Yes. So that's why if we are going to write on the position 64, this is like position 32 at the end of this. Then we have, this is the position 64. So this is where we want to write, in this position. Like the cursor is here in the position 64, and we want to write 1 byte, which is this byte, like the 80. But you are not writing it here, because as we said, it's just chunks of 32 bytes. And what happens if you only have 1 byte? That we can like path left, like all the byte here, that the 31 byte that we're missing. And as you know, like on any on binary or decimal or hexadecimal, like any zeros that you add to the left, that doesn't count, right? It's like the same number. Okay, so after running this, let me put this here. after running all this code, which is this bytecode, this is what we got, So now we know what this code is doing. I mean, we know it's initializing the memory this way. So this is like a memory initializer for some reason. Now the answer is, the question is why? Why are we doing this? I mean, we know what we are doing, but we don't know why, right? So the question, the answer is also on the EVM specification. And this is saying that here, the first 64 bytes, you have something that they call a scratch space. And it's something that is used sometimes when you do some, that sometimes you can do like inline assembly on Solidity, some inline assembly. Yep. So this is used for that. Then you have something here that I'm not going to reveal yet, because I mean, this is like the surprise, the final surprise. And then we have another 32 byte here, which is called like the 0 slot. So you don't have to, you shouldn't write here ever, but this is used for the default value of the dynamic array. When you have like a dynamic array, this is like the default value. It's always 0, but you shouldn't write here. So this 80, if you remember, that the 80 is like 128. So this is 32, this is 64, this is 96, and this is at the end of this is like 188, like 28, right? So if you see this number is this number. So
it's sort of pointing to the end of the 0 slot.
Yes. So this is actually called the free memory pointer. So this is always pointing to the memory that is free. In this case, is this here. If you want to write something in memory, it's going to be here after this 0 slot. So for example, if you have, imagine that if you, in your Solidity contract, in one method, you have something like uint, and you have like a fixed array of 2 and memory, and you have like my bar. You can have that. You can initialize this in your method. So what it's going to do is going to initialize this 2, because we have like 2, right? It's like the value, the size of this array is like 2. So you have 32 bytes here, and it's going to initialize that with 0, and also is going to change this number. It's going to update this number. I think it's going to be like C0, which is like 196, and it's going to be pointing here. So now we have our answer, right? Like this, when you see this on the bytecode of the smart contract, this is just the initializing the free memory pointer in memory, right? So that's what this is doing. I don't know if this was like confusing or not.
That makes sense. No, that makes a lot of sense to me. Yep. So just to say it over again, basically you see these few bytes, and the bytes basically set up this scratch space and then a pointer to where the free memory is, and then there's a 0 slot, and the free memory points just to the end of the 0 slot. And then as you do more things that are going to mess with your stack, stack or memory? It's the
memory.
Same thing, right?
No.
Yeah.
In this case,
it's different.
Memory.
Okay.
Yeah.
Okay. So as you mess with your memory, that free memory pointer is going to bounce around and point to other things. But what you need to do is initialize it to just after the 0 slot, and then you'll use it from there, and you'll go from there.
Yeah, and
just like an initializer.
Yes, it's initialized. Basically, it's initializer. Some contracts are different, and for example, here instead of 80, they have like a C0 or something, because they have done something on the
there's more 0
or whatever, so they have like more
padding.
memory allocated.
Yeah.
So that's why they start in a different position. But yeah, this is just like a free memory pointer. So now
we know. I get it.
Mystery solved.
Yeah, so far we got ways to go, but I'm with you and I'm following you and I get it. Thank you for this so far.
No, I think it's always when you are like learning something, like having like this, like something that you want to know why is this way. I think that's like the best way of learning, right? Like trying to investigate and research why that's happened. So yeah, I mean, yeah. Sorry.
I was gonna say, so I have not checked before. I didn't actually realize that number. I'm one of the persons which didn't go to Etherscan and look how the contract starts. But now it kind of really makes sense that it's pointing to the place where the contract is actually like where there's free memory to actually deploy the contract, I guess. But yeah, that was like a really good intro to a very technical concept and a very high level. So appreciate that.
Yeah, thank you. So Austin, do you want to do like any of these like function selector stuff?
Yeah.
In your Skype, something?
Yeah. So I can take over. Basically, I have. Here's a smart contract that I've deployed. I just wanted to show the difference between bytecode and a function selector. So here it is.
You see that's the magic number.
Yep, that's the magic number right there, to the 52, right?
Yep.
And now
maybe
I know
can
what
we
it's
make
doing
it a bit
there.
bigger, like the input
Yeah.
section?
How's that?
Nice. Yeah.
Better? Way better.
Yeah. So there it is. So then we know that the rest of this stuff are operations that are moving memory around or adding two numbers together or subtracting numbers or, jumping to a place and then setting that place in storage. But if we think about it, this is like a stupid simple computer. This little computer is just like jumping around and setting memory and reading memory and performing simple operations on that memory.
Yeah,
is that a good way to say it?
Yeah, like basically it has like we saw like this like pass, like push one and Mstore, like that's like two different instructions. So the EVM only has like 140, I think. So this like computer only knows 140 things to do, 140 instructions. So that's simple, right? It's like 140 things.
It'd be easy to run, and we want the EVM to be very simple, right? The more simple the EVM is, the more decentralized Ethereum is, because more people can run them in their house, right? If it was a supercomputer that everyone had to run to stay in sync with each other, then they wouldn't be able to do that. So having the EVM be a simple machine helps us both on security and just on decentralization. So, okay, so here's what I want to show, just the difference. I was showing it earlier, but I don't think it was clear enough when I was showing it. So in this case, so first of all, everything's a transaction, right? And in this transaction, here's the transaction ID. Basically, I send it to no one. There's no two. It says contract created, but if we were to actually look at the transaction, the two is actually empty. It's null. And then we see this 0x, we see this as the bytecode. So basically this transaction is putting all this information on chain. That's all I'm doing in this transaction is I'm taking all of this information and I'm writing it to the blockchain where everyone else can read it, okay? But that's what I'm doing is actually creating a little program, right? And then once that program is up there, it has its own storage slots. It has things that you can interact with. How do I call a function on this program? That's the next step, right? So here's another contract I have, or here's another transaction. This is the transaction hash. Everything's a transaction. In this case, I'm talking to this contract. So this one has a to address, and the to address is this contract. So I'm sending this transaction, and it's getting mined into the chain, and everyone's seeing that it's like I'm sending money to the contract, right? But I'm actually not sending any money. I'm only sending data. And if we go look at this data as the original, okay, so we don't see the 06F stuff, right? We see this, and then we see this, right? So it's what, 8 bytes? Is that right? 4 bytes of data? Yeah, what? 4 bytes of data. 1, 2, 3, 4. These 4 bytes of data right here, they're not a contract being deployed. So what are they? They could technically be a message, right? Alice can send a message to Bob by just throwing some data into the data field. We can deploy a contract by throwing, this out here, right? But to talk to a contract, you actually send a transaction to the contract. And in here, you have what's called a function selector. Now, we can see it's nice enough that it decodes it for us. And I think it shows it somewhere here. Let's see if I view input as default view. Yes, this is actually calling this function. It's calling set subnode record, and it's sending in all these arguments. So we have what here is the method ID. And where do we get that from, right? Well, I have this ETH build set up here that shows it. Let me zoom way in on it. But if I take that same text and I lay it out into a string, and I say set subnode record, that's the function I want to call. And we have a bytes 32, then address, and then a uint64. Those are the argument types, right? So I have the name of the function and then the argument types in parentheses. Now, if I hash all of that, then look what I get. Look at this hash. Look at these first four bytes here.
Yeah.
Do I have those? Yes, there we go. It goes 5 EFs 2, then C7 F0, right? Basically, the hash of this message cut down to 4 bytes is what's called a function selector. It's me saying, I want to call this function on the contract. So I send a transaction to the contract, and I put these first 4 things in there. And then let's see, let's go back to that. Those first 4 things are in there, right? Let's go as original. So there's the first 4 things. Then all of this stuff is basically the parameters encoded. So each of these things, the bytes 32 that you need, the address, the uint64, that's all encoded in here. And usually it's just one after the other. If it's a bytes 32 and then a bytes 32, you're just going to go 32 bytes and then you're going to go another 32 bytes. And notice you'll see this padding, right? So this is an address. This is probably my address, 3A44, but it's padded with these extra zeros to make an address fit the bytes 32. And basically they just stack them in there. If it's a bytes 32 and then a bytes 32, you can just count the first 32 bytes as the first one. You count the second 32 bytes as the second one. The third 32 bytes as the third one. Now you mentioned dynamic arrays. And I don't know exactly how this works, but I think there's like basically a number that says, hey, this is a dynamic array. And then there's another number that says, hey, it's this long. And then you go for that many reading multiple bytes. So that's how you do like a string or a bytes array, something that might be dynamically sized. You basically say, this is the type of the thing, this is how long it is. And then you can go read for that many more words. And that's how you get a dynamic size. But just to zoom out one more time, there's basically deploying a smart contract. Like I can send, so Austin sends $5 to Edda. There's going to be a to, a from, and a value. There's not going to be any data there. I can even say like hearts, hearts, hearts in my data field if you want. You can send messages to people. Then there's actually deploying contracts. And that's marked as kind of this. And that's going to tell you that all of this is actually going to have, this is now going to have a new address on chain. It's going to have storage that everyone needs to keep track of. And then if someone sends a transaction to this new address, they can actually execute a function on that contract. And the way you select what function you want to call is by doing this kind of like hash method to find this, and then packing in the rest with all your arguments. So by doing this, we have this really cool blockchain that lets us just send transactions. But on top of that abstraction, we're actually like running a little computer, and we're deploying little programs, and we're talking to those little programs, and we're doing it in a way that's completely decentralized, and anyone can deploy a contract, and anyone can talk to those contracts, and there's no central figure that can like turn those programs off. So that's what I wanted to dive into to show that off. Anything else we should look at, Carlos?
Yeah, one thing. Can you go back to the transaction with the data, like the?
Yes. So here,
can,
right?
Can you copy like the first 4 bytes? Yeah.
This stuff.
Yeah.
Send it to chat or something.
Maybe without the 0x at the beginning.
Okay.
Only like the and then copy that. And can you go to the contract to this contract?
Ooh,
the contract that
yeah. So let's see, what contract are we calling? This is the ENS registry.
Yeah. And go to contract. The verification, and you can see the bytecode there. If you just scroll down, you will see the bytecode at the end. No,
let's see. So there's the 60, 80, 52. Yep, there it is.
Can you search for that string now?
Yes, there it is, right there.
Yeah. So this is actually like the logic of the function selection is embedded on the bytecode. So that bytecode will say, okay, is this the cal data is equal to this function signature? No? Okay, keep going. And when you say yes, you will jump to where that function is, and it will run only like that portion of the bytecode. So that's how that maybe we can do that like another day, just showing how the bytecode do like the function selection internally, which is also like super interesting.
I think probably like a great demo here is we would build a smart contract that just like has a piece of storage, and when you call a function, it adds some argument to that, like just adds 5 to it or something like that, right? So we deploy the contract, and it has a storage of 0. and then we can call an add function or a subtract function, and it's going to subtract from that. So we could see the bytecode, we could see the function selectors. I think that would be a cool way to deep dive. And then maybe we could have the EVM on the side of it. I think this has been like an intro, but I think if we want to do a deep dive, maybe we could do something like that where we're stepping through each thing and we're kind of jumping around. But hopefully this has been kind of like a good high level of what's going on here and how the heck you would create kind of like an app platform that runs on top of a blockchain, and how you would do that in this way, and how you would have, well, you have a little EVM and everyone has a little computer, and all these transactions are kind of either deploying another little app to that computer, or they're calling a function on one of those little apps, or they're just sending money around. But this data field is super powerful, right? I think that's this data here. Let's see if we go find the transaction that deployed this. This data field is super important. Input data, right? Like this is the key to everything. This is the whole program and how to operate, how to run all those things. So cool.
Yep.
Awesome. Good intro to EVM. Are we missing anything? Any final questions? We could dive in and do some more, but I think that's a great, we're going to scratch the surface of the EVM, give you a high level, and then kind of tinker with it. Any other things to add?
No.
Thank you, Carlos. You know way more about the EVM than I do. I love that. I need to learn some more.
Thank you, Carlos and Austin. I'm learning some more.
Yeah, I think next episode is going to be all ERA.
Yep.
All ERA.
Yeah. We need to stop mansplaining so much.
We can. We'll see on the next episode, but
and probably a huge hat tip to the people that came up with this, right? The folks that built the EVM and built how, all of this works together. I could have never come up with this. And it's so cool to be able to all I have to do is write some simple Solidity, and I deploy that, and I don't know what happens. It goes, and then everybody can talk to my app. From a high level, this is really powerful for me as a programmer, because I can write a simple program and anyone can interface with that, censorship resistant, and it's up forever kind of thing, an unstoppable app. It's so cool.
Yeah, thank you. Yeah, thank you to that people. I mean, we are saying all the time that this is super easy,
so
super
cool.
Dumb machine. Yeah. But I mean that's like a dumb, a simple machine, because this super smart people build this, right? But make everything super simple, but it is not simple. I mean, the people who build it, yeah.
It's like if you really understand a concept, you can explain it simply, sort of. Or if you want something to be very secure and decentralized, it needs to be a very simple thing that does exactly one thing really well, right?
Yeah.
Very cool. Awesome. The EVM, everyone. Awesome. Thanks, Etta. Thanks, Carlos. This is a good one.
Bye, everyone.